Hello everyone, this is Dr. Young, and this is a short video on neutralization reactions. They're just a type of acid-base reaction, but they just have a special little name that we need to know. So remember that before we talked about acid-base reactions, where an acid-base reaction is just a transfer of a proton from one species to another one. And we defined, right, remember that we defined an acid as a proton donor, so acid formulas usually begin with an H. And bases are proton acceptors, right? They're H plus acceptors. And we also mentioned how acid-base reactions often, but not always, but one way to see them is as double replacements. The key thing is that you transfer proton, but oftentimes, especially in like Gen Chem and stuff like that, you see that there's double replacement. So you replace the H plus of one thing with the cation of another thing to get two products. Now, neutralizations, they are acid-base reactions, right? So first of all, let's get that out of the way. They are acid-base reactions. They're just a subset of acid-base reactions. And so here's an example right here. Nitric acid plus a potassium hydroxide makes potassium nitrate and water. Now, for neutralization reactions, they're called neutralization reactions because you're going to end up being neutral. And by neutral, we're talking about the pH scale. So this is not a video on the pH scale necessarily. We're going to talk about the pH scale in general chemistry later. This is just introducing this type of reaction where if you're talking about water as a solvent, you go from 0 to 14, and 7 is right in the middle. That's considered neutral. So, waters are around here. Ocean water is a little more basic. Rainwater is a little more acidic, but water's around here. Your blood's at 7.2, but this area is considered pretty neutral. Lower is more acidic. Higher is more basic. Don't need to know that yet. But the only reason I'm mentioning it is that that's why neutralization reactions are called neutralization reactions, is because the pH, the acidity of the solution, ends up being around 7, and you have a neutral solution, right? Where before the idea is you started with something that was acidic, so you had low pH. You had something that was basic, so you had high pH. You mix them together, and you end up with just water. And it's just a nice neutral solution is the idea. So that's one key point. Another point that's going to be more helpful down the line is that these reactions always release heat. They're always exothermic. Right now, we're not talking about exothermic reactions or thermodynamics or anything like that, but just wanted to mention that they release heat. So you want to be careful when you mix acids and bases because they will produce heat, and you could boil your water, for example. Like I said up above, neutralization reactions are just a type of acid-base reaction, right? They're not different from acid-base reactions. They are acid-base reactions. And the way to identify them, which is the key for us right here, is that the one reactant is a strong acid, the other is a hydroxide salt, and water is the product, right? And so if you look at our equation, we're saying water is a product, check, right? I have water as a product. We are looking for one reactant being a hydroxide salt. So it needs to have something with hydroxide in it, right? OH minus, which we do. In this case, we have potassium hydroxide, but it could be sodium hydroxide or lithium hydroxide or something like that. And then the third thing we're looking for, the other reactant needs to be a strong acid, right? So the other reactant needs to be a strong acid. In this case, I have nitric acid, which is in fact a strong acid. It is a strong acid. You probably don't know that at this point yet, especially if you've never had chemistry before. So we need to talk about what are the strong acids and what make them strong super briefly so that we can identify a neutralization reaction, right? Because what we're looking for is we always have a strong acid. We always have some kind of hydroxide species, and we always make water. That's how you identify neutralization reactions. Now, strong acids, again, we're not getting crazy into acid and base chemistry yet. This is just a little introduction to it, but strong acids completely dissociate in water. That's what makes them strong, is that they completely dissociate in water. And what that means, right, is that when you take your strong acid, like hydrobromic acid, for example, it starts off with a hydrogen bonded to a bromine. And again, don't worry about the bonding stuff yet because we haven't gone into it too much. But the idea is that afterwards, that bond is broken, and now you have an H plus ion and you have a Br minus ion. You have two separate ions. They've dissociated. They're no longer connected by that line, by that covalent bond. They're more ionic now. Now, to say that we're completely dissociated means that once you put hydrobromic acid in water, that basically you end up with like 0% of this starting material. So this is essentially 0%. And over here on the right-hand side, the H plus and the Br minus, this is about 100% of all of that, all those H's and Brs. They're all dissociated. They're all split up in water. They're all fully dissolved. They're broken up. They're dissociated. And we'll see that that's not true for weak acids. Now I put here just hydrobromic acid, aqueous hydrobromic acid splits up into H plus and Br minus. I am okay with that. You might also see though HBr and then people will write plus water, like it's a reactant, and that gives you H3O plus and Br minus. So either of these is fine, right? These are basically saying the same thing. So I'll write that. Say the same thing. So you might see this or you might see that. They're considered to be equivalent. The difference here is that this is just the proton, right? This is just a proton, an H+, whereas H3O+ is called hydronium. And the reason why people sometimes use the bottom one with water and call it hydronium is that there's really no such thing as like a free proton. It's going to be attached to something. But again, we're not really into bonding yet. So that we'll talk more about that later. But an H+ really doesn't exist by itself. So a lot of people say H3O+ and say, oh, well, that H+ is actually attached to a water molecule. And so we have H3O+. That represents the acid, the H+. Now, if you continue to be my student in the future, we will also talk about how hydronium is also not a real thing. There's no such thing as an H3O+ molecule. But that's kind of getting beyond where we need to get right now. I will stop getting distracted. These are two separate ways to say the same thing. So if you see either one of them, this is considered a dissociation of a strong acid in water. Now the difference down here, right, like we were saying, is that weak acids, so like hydrofluoric acid down here, hydrofluoric acid's a weak acid, and that means when you put it in water, it does not completely dissociate. In fact, there's about 1,000-to-1 ratio between these things and that thing. So only like 1 in 1,000 actually dissociate. It's not that much. So we consider it a weak acid. It doesn't have that big an effect on the acidity of a solution. So we have strong acids and weak acids. That's kind of what they mean in general. Now, what you need to know is you need to know these, right? You need to know these strong acids. These are the 6 really common ones. It is not an exhaustive list. There are lots and lots and lots of other very strong acids out there. But these are 6 common ones that you will see most of these in Gen Chem lab or OChem lab. And these are just really common ones that you see throughout chemistry textbooks and online and stuff like that. So these are very common ones that you should know. You should just see H2SO4 and be like, that's a strong acid. You should see HCl and be like, that's a strong acid. If you see things that are not these at this point, just assume that they're weak. And why do we need to know that? So that we can identify neutralization reactions, right? Because remember what we're looking for neutralization reactions is we need a strong acid. Let me do this in black. We need a strong acid as a reactant. We need some sort of hydroxide species as a reactant. And we need to make water and something else. It doesn't really matter what the other thing is, but that's what I'm looking for my neutralization reaction. Strong acid, hydroxide, mix water. So if you get a question like which one of these represents a neutralization reaction, that's what you're looking for. So I'd go down to here and I'd say, okay, well, my first one, I see hydroxide, check, I've got the OH. I see HCl, that's a strong acid. I know it's a strong acid because here it is, it's number 5. And I've made water. So this must be a neutralization reaction. I've got a hydroxide, I've got a strong acid, I made water. So I want you to pause for a second and look at these last 3 and decide, are all of them neutralization reactions? Are only some of them neutralization reactions? So go ahead and pause and we'll come back to this in 1 sec. Okay, so if you look at this, I see that I have hydroxide again, good, check, and I have HF. But HF, hydrofluoric acid, is not one of these. And since it's not one of these, I'm assuming that it's a weak acid, which means this is not a neutralization reaction. The pH of this solution when it's done is not going to be neutral. It's actually going to be a little basic, but still, it's not going to be neutral. If I look at the second one, if I look at C, I have H2SO4, which is a strong acid, check. And I have this thing right here, but that's not hydroxide. It's not hydroxide, so I know that this also is not a neutralization reaction. It's not a neutralization reaction because I don't have hydroxide. Now for the third one, I have sulfuric acid, check. I have a hydroxide, check. And I have water as a product, check. So this last one must also be a neutralization reaction. That's all I want to say about neutralizations. They're just a term that are going to be thrown around. If someone says, write the neutralization reaction between hydrobromic acid and potassium hydroxide, you want to know what that means. So that's all. Study up, watch the next videos. Good luck.